Uncle Bob says he is taller than 80% of all men. Assuming he actually is in the 80th percentile in height, how could you estimate how tall Uncle Bob is? Assume men have an average of 70 inches of height and a standard deviation of 5. Okay, so trying to find out how tall he is, we're trying to find the x value, right? We have the mean, we have the standard deviation. Now, when they say he's in the 80th percentile, if we would draw a picture, and we say this is Uncle Bob, right? We don't know how tall he is, but that's where he is. If he's in the 80th percentile, that means the area under the curve is 80%, or 0.80. So when you look at your z-score probability table, we're saying the probability is 0.80, so you got to work backwards. So you go to your table and you're like, where is the closest probability of 0.80? And hopefully you find the z-score of 0.85, right? Because that's the closest. It's not exactly 0.80, but it's the closest we have. So we know Uncle Bob has a z-score of 0.85. So now I can use my formula. Z equals x minus mu over sigma. So z-score equals the value that I'm trying to find minus the mean over the standard deviation. Well, if we just, solve this, I multiply both sides by 5 to cancel these out. So that gives me x minus 70 equals 74.25. Nope, that's not the right answer. That's my final answer, 4.25. Then I add 70 to both sides, and that gives me an x value of 74.25. And that's inches. So that's roughly, in case you care, 6 feet, 2.25 inches is how estimated height of Uncle Bob. What proportion of men would we expect to be between 5'8" and 6'4"? Well, first thing you got to do is figure out inches. 5 feet is 60 inches, plus 8 gives me 68 inches. 6 feet is 72 inches, plus 4 gives me 76 inches. So we're looking at what proportion. Okay, so I'm looking for, remember, the mean is 70, and the standard deviation is 5. So the first thing we're going to need to do is we're going to need to find z-score for these two values, because we're trying to find this shaded area between them. Okay, so first I have 68 minus 70 over 5 gives me a negative 0.4, so that's here. And then 76 minus 70 over 5 gives me a z-score of 1.2, which is here. Now, we don't have a mechanism for finding the area between, but I know that I can find this area, right? Everything to the left of 0.4 is 0.3446, and everything to the left of 1.2 is 0.8849. Well, I need to find a way to only have this piece here. So think about it. If I would subtract green minus black, the piece that overlaps would go away, and I would only be left with the piece in the middle. So that's exactly what I want to do. 0.8849 minus 0.3446, and that gives me a probability of 0.5403, which is roughly 54 3/3%. That's the proportion. So 54% of men would be between 5'8" and 6'4". That's what this tells us. Suppose the average U.S. income is $47,000 with a standard deviation of 45,000. How many standard deviations from the mean would someone who is in the top 1% earning $380,000 a year? So how many standard deviations? They're just asking for the z-score. So the z-score is value 380,000 minus the average of 47,000 divided by the standard deviation of 45,000. When you find that, you end up with a z-score of 7.4. So that is 7.4 standard deviations above the mean. Get off of there. If the top 0.1% of the U.S. population earns an average of 1.2 million, what is the z-score for that person or those people? So 1.2 million minus our average of 47,000 divided by 45,000. That z-score is a whopping 25.62. Okay. Now, is income in the U.S. normally distributed? How can you tell from the z-scores? Okay, now if you look, top 1%. So top 1% means over here is 0.01 and over here is 0.99, right? That's what this means. So if I look at my z-score table probability, and I find something really close to 0.99. That's going to give me a z-score of approximately 2.3. That's what my z-score table shows me. But remember from that last problem, we just saw that this is from part A. From part A, it said that the top 1% have a z-score of 7.4. So we're comparing 2.3 compared to 7.4. That's not even close to being the same. So the answer to this would be no, because in order for this to be normally distributed, the top 1% should be roughly 2.3, and it might not be exact, but 2.3 and 7.4 are not even close to being the same. So I think it's important that we can recognize U.S. Income is not normally distributed. And then you can see it in this graph. So this is the graph of the distribution of income in the U.S. for 2011. So it's probably changed in the last 7 years. But if you look at this, it tails to the right. And what does that mean? Well, if it tails to the right, that means it's skewed to the right.